Hello, can you hear me now? Good. Okay, so if you're okay, we can start this. So, well, welcome to Introduction to PyTorch for Data Scientists. You are going to be the first cohort that's going to actually listen to this talk. The first part of this talk is going to be basics, and the second part, we're going to do the hands-on. I'm assuming that nobody, not even the guys that are looking at this in the YouTube channel, know anything about machine learning or deep learning. Okay? So, with that, let's start. So, for those of you that don't know me or you haven't been in the workshops lately, my name is Dr. Didier Barradas Bautista. I am one of the two data scientists in the KBL team. This is our team, led by Sohail Ghani. We have different expertise. Actually, we can also dabble into VR or high throughput visualization of data. So, just a little bit about my background. I am not a computational scientist by training. So, just to say, like, the way of life, it takes you different places. I'm actually a molecular biologist that started the path because he wanted to do a fluorescent bunny. Yeah, that happened a while ago. But given that the biology field is also very data intensive, it led me, technically speaking, into computers, then into HPC, into AI. And here I am giving this talk about, well, deep learning. So I was just asked this question: why PyTorch, right? Like, what's the deal? In this graph, you can see that PyTorch, which is the big red thing, is very popular among all the papers that actually give the code back. And on this very graph, also, you can see in this place here, a bunch of other languages that people can be used. For example, a while ago, a really long time ago, Cafe 2 or Coffee 2 was something that actually was part of the frameworks that people use to code deep learning. This is one of the predecessors of TensorFlow and PyTorch. Actually, you can see here also Torch, the original implementation of the deep learning library. It was not PyTorch, it was just Torch. So the Py comes because the engineers at Fair AI or Facebook or Meta AI, however they call these days, they translated all these things into Python, and then they opened basically the market for it. TensorFlow is also written in Python, and this is why it's the second place you see here. But as you can see also here, over the years, the usage is less and less because PyTorch gives you more flexibility. It allows you to tweak some details, okay? And then there are others. For example, JAX is also a product from Google. JAX is, technically speaking, the next iteration from TensorFlow, okay? So if you're going to learn something, probably JAX is the way to go about deep learning, machine learning, or everything, if you believe in Google or you want to dabble with it. But we're going to focus today on PyTorch, okay? So, deep learning concepts. I'm going to assume that no one has a think about, deep learning. And I'm going to use some very nice slides, which are coming from the machine learning flashcards from Chris Albon. Chris Albon is also a data scientist. His background, I think, is sociology. He's not from the computer science. Okay, so data science is something for everything. You can apply it to anything, not only, our kind of science, engineering and stuff. He could. I mean, he's dabbling a lot with it. Yeah, he also doubles with deep learning and everything, but he's very pedagogic, and you will see. Yeah. So, for example, what's machine learning? One of the questions that I should ask you is like, I guess, have you ever seen a small kid learn, like your brother, your son, whatever. So, a toddler or a smaller child has no idea what to learn. And depending on who you ask, the definition of learning changes, because learning for some people is one thing, for computational science is another thing. For example, for Jan LeCun, he said, like, for learning something, vision is the primary source. While for other persons, they will say, like, no, it's language. You teach a child first how to speak, but then you can counter, well, the kid knows how to see naturally first, right? It depends. But let's say that we abide by this kind of situation. Like, we have a computer program now. We want a computer to learn. What does that mean? We have some set of data points. So we have to go through all these data points. And then we have to measure how that performance is in the, let's say, after the training. So this is why for a computer program is a different definition. For a computer program, it's like, how good is my data set being represented by this computer, and then do a prediction. So it's not like learning like we're doing here in the university, like you get a degree and then you get basically a score or something. This is kind of different because it's not just a data set. You as a scientist have to like learn a lot of things. This is why you're here, as a matter of fact. So you have a very large range. The human brain is actually pretty malleable, especially when you're early. So what's the starting point? Like I said, you have a bunch of data sets. So here we have to talk about three things that are the sacred things. This is like your cornerstone. You have to have a training dataset, a validation dataset, and a test dataset. Those are like the three things that you need. Usually, people struggle to have a test set because this has to be something completely out of the picture. But let's focus on this plot. In this plot, you can see you have samples that are circles and X's. Then you have a computer program. You train this program and you say, okay, give me the best way to divide these two things that I have there. Two things can happen, and that will happen to you too at some point. So you either do a computer program that is so good, but so good at dividing the things that does the red line you see there. The red line is called overfitting because it does a perfect division, but then when you give in a new data set and you flip the data set, for example, for the X, instead of X's is circles and vice versa, the program will completely fail because it's not actually dividing by class. It's really struggling. The performance will crash. On the other hand, you can train a program that is so lazy that it just draws a line. And that line divides badly in general because it's not really fine on how it divides the data set. As you can see in that blue line, you have a lot of the X's in one side that is populated mainly by the circles. And then you have some circles on the other hand. That's bad performance, sort of. But sometimes that's the only performance you get from that training data set. It depends what you do and the strategy you take, okay? But usually, a lot of people does overfitting. If you are in the computer news nowadays, you know that LLMs are all over the place. And there is a competition for that, right? There is a benchmark where you train an LLM, you put it there, and you see how well it performs. Right now, Meta is on, they trained something called Llama Maverick, and the performance was so good, really so good, blown out everybody else that it was like very suspicious. Like, hey, here, this is too good. He's dividing the data points really well, suspiciously really well. So many people argue that it was overfitted to the actually testing data. And this is why they had like the best score. So this is something that you should take care. Okay, but what is deep learning? That was the starting point, the training, the testing and the validation. That is what you have to do with your data points. But deep learning refers a sub-branch of machine learning. Now, deep learning is really, really, really good when you have either text or images. If you have a tabular data, meaning columns and rows, you're better off with any technique that is like from the classical side, linear regression, binary classification, random forest, and so on and so forth. There are many of those. Deep learning is not going to be better than those ones when you have basically columns and rows. But when you have high dimensional space data, and I will talk about that in a minute, what does that mean? When you have basically something that you can imagine as a word of a string of words or an image, deep learning can be your choice. And why is deep to start with? So if you see there, we have a shallow network. The idea of a shallow network is like you have your input, which are the squares, and then you have a layer of neurons, which are the next layer of circles, and then you have an output, which is the last one. That's a shallow one, because it's just one layer of things that are interconnected from the input to the output. That doesn't suit well for computers. As a matter of fact, for a computer, the best idea is at deep learning. You have different layers of a number of neurons, a number of circles that are highly interconnected between them. This is why it's called deep, because you can go to many layers. Now, the problem with that one is like, because all the circles are interconnected with everything, that's why people say it's a black box, because you cannot track down exactly what happened to every single one of the circles until you get to the output. So this is the thing. What is highly dimensional? What do I mean by that? The best example is an image. So if you know, or if you don't know, what is a tensor? A tensor, technically speaking, is a matrix of matrices. I know you probably didn't see this on any regular math course because I didn't see it until I was downloading this. So if we take, for example, an image, you know actually this. An image is a combination of 3 channels, the 3 normal colors, blue, green, and red. And that can be actually represented by matrices of numbers. How red is that red? So you have 3 different matrices that they call channels in the visual context. And then it can be very large. Those are your pixels. Each of these squares are those super megapixels that you have in your iPhone or your Oppo phone or whatever. This is, technically speaking, what they are talking about when they say high dimensional data. Because we can have as many as these layers as you want. For example, in biology, you can have matrix of expressions of 1,000 different patients. So those are different matrices of numbers of all different genes from 1,000 persons. That's highly dimensional. So how do you divide all that data? Because this is not just circles and crosses. It's like a bunch of numbers that are overwhelming. So that's why it's needed something more advanced. However, at the beginning of time and before I was actually even born, I don't think so, but I'm very old. Anyway, so the starting point in all data science, well, all deep learning history was sets like this, the MNIST dataset. So take notice that it's 70,000 handwritten images like this. This is the actually most simple way of representing an image because it's a black background. It's a white background with a black thing. And you can represent that number or these numbers with pixels. And those pixels can be a matrix of numbers where those numbers represent 1 if it's completely black or 0 if it's completely white. And whatever in between, which is gray, is a number that is like how black it is. Okay? So this was the starting point for all developments you have seen now. This is a classic data set. And when you go, and in theory, the computer scientists should know this. It's like, oh yeah, I'm training something in the MNIST data set. Like, but that's already done. Why are you doing that? Like, for practice. Yeah, yeah, handwritten digits. Okay. So they actually, I think they compile a lot of different. The origin of the dataset, they went over at some kind of office in United States, and they scanned everything, took photos of all the digits, and then basically passed them into this kind of arrays. So it was 70,000 of them. You have 70,000 of these kind of solo images. So what's the question again? What is the pixel? Aha, we have the 70,000 samples. Okay. So this is just the data set. So what we're going to do is basically you have 70,000 and then you have to divide it in 3 different chunks. You have to divide most of it into a training set, a big part of it into the validation set, and a smaller part into the test set. And then the computer will read the matrices, and then we will see how we will train, theoretically, a neuron, okay? So, for example, in deep learning, they call this a neuron. So in this case, the inputs for the handwritten dataset will be each of these squares. Each image is going to go to something that is called a neuron, which is depicted there in orange, that it says sum, okay? And then you have something called activation, and then it gives you an output. That output could be a probability of what is that input saying. But, okay, one step back. This is a neuron, okay? This is the way everybody represents a neuron. The neuron has a couple of things. It applies weights and biases for each input, and it does a summation of all those matrices. And then it has an activation function that is called let's say that this is a filter for the neuron to be active or not. You will see it in a minute. But I also want to give you the lingo. So when you are talking to a computer scientist that knows this thing, you have an input layer, then you have hidden layers, and then you have an output layer. It's hidden because between the input and output, you don't know what's going on, but it's a bunch of mathematical summations from all the matrices, adding weights and biases, and having an activation function. So each of those red things happen to have this kind of architecture, and the information is going to flow from the input into each of these different circles in completely different random ways. Okay? Yes, each circle will have different weights, different biases, and different activation functions. As a matter of fact, something that I like to highlight is like there was or there has been always this nagging question from the good people that does statistics. Is like, isn't that deep learning just purely statistics, like glorified statistics? And the answer is like, no. Kind of, but no. So at some point, it's like people is thinking like, yeah, but this is very simple, right? Like, yeah, if you think that this is a linear regression. If you go back and remember how to draw a line in the Cartesian space, this is the equation. Like your y point is defined by the intercept, the slope, and your x point. And each of those elements are here. Your inputs, you have it there. That's the x over here, the squares. The weights are now the slope. And then the intercept is the bias. So all the elements of a regular linear regression are there. But there is another thing. There is the activation function. And most of the friends from statistics doesn't account for that when they're saying, like, it's just statistics. No. There are a bunch of other things that you're not seeing. But yeah, if you're a good statistician, you probably can replicate this. Now, the thing with deep learning is like, if you see on your right-hand side, this can be actually interpreted as a bunch of matrices. So if you remember from your linear algebra, you can do matrix multiplications very quickly depending if you have a vector and a matrix, and so on and so forth. In this case, you can have a bunch of points that you want to predict, which are your y. Then your x, your predictor, is all the bunch of different points in your matrices. That will be multiplied by the slope, which in this case are the bias. And you have also basically a vector there with a bunch of values. So there is a bunch of mathematics operations going on at the same time. But again, there is that thing called activation function. So as you see here, your input starts, and then they go all into the neuron. The neuron does the mathematical function it's supposed to do there, which is kind of a linear regression. It adds a bias. But the activation function changes that. The activation function, think about as if this is going to be passed to the next layer or not. It's a filter. In this case, I'm showing you the hyperbolic tangent. So as you see there in the animation, it goes from -0 to +1, -1 to +1, sorry. So at one step, it's like, okay, so it goes all the way to -1. And you can see that it goes back and forth, back and forth. We will see that this is called actually backpropagation. Now, why I'm telling you this, because the activation function and the mathematical function you have there to sum out everything will change according to your needs. You can change that. There is no one activation function that rules them all. There is no Mordor here. So in that case, the activation function basically acts as a filter to say, like, this neuron is going to stay active or not. And that happens in all the neurons across all the layers, and then it becomes a mess to track down, because you cannot track every single change every single time that this goes over and over and over for the iterations that you have to do. And now I can also add there that the bias, it depends how hard you are, but the bias allows your prediction to be flexible. So the more bias there are, probably the less likely is to be, how is it, like, the model will not generalize properly, because the bias is how easily that line that adjusts all the data points bends to the next data point that hasn't seen. All right? I hope this is clear. I'm trying my best to explain. Yes, one question. Yeah. Like I said, like, it seems linear. Like I told you, like, there is components of a linear regression here. But the activation function doesn't have to be this one. It's just an example. As a matter of fact, the activation function preferred for everybody in deep learning is called rectifier linear unit, ReLU. Because this approximation usually leads to a mathematical problem that is called vanishing gradient. What is a gradient? I will tell you what is a gradient. But first, we have to take control of what we are doing. So a thing that I have to tell you is, like, you don't just start from zero in every sense. Each of these neurons actually have to be started with a random number there for all the weights. So it can actually start trying to fit the data with all the equations that you have there. So random initialization is very powerful, because if you, by the way, in a code do not define this, every time you run that code, it will be different. You will have a different result. So you have to control this specifically initialization first. This is why I'm bringing it up. So what type of activation function we will use in a nonlinear regression? I can tell you, there are different types of activation functions, like the leaky ReLU. There was one that is cross entropy, because, for example, if you have literally a binary classification, is true or false or whatever, there's a linear regression for that. It depends on the end result that you want to have. Do you want to have, for example, a number, which is a probability, you probably want to go to leaky ReLU, or even ReLU, the normal rectified linear unit. So that depends. It's case by case, but we will explore one of them only in this moment. So as you see in the animation, it goes forward and it goes back, right? You see that the weights go forward first and then the weights go back. That's called backpropagation. And this is where something called actually loss function enter the lingo. Now, the backpropagation also needs a strategy. The backpropagation doesn't just happen. You have to define what do you want, what kind of a strategy do you want to go back? Because going forward is like just feed the data and basically activate or deactivate any number of the neurons. When you go back, because you're going to update all those weights and all those biases, that's when you need a different strategy. You just cannot go all the way back just because you don't know actually what path you took. Mm. Yes. So the question was like, when you have, for example, 4 layers, you go all the way? Yes. From the last layer, you go back into each of the different layers. And in all different layers, because you go iteratively here, you will have some that have been activated and some neurons that have been deactivated, but you don't know the path back. You just know that it happened. And this is why you need a strategy. But now that you mentioned that you go first all the way down, there is something that you also have to add to your lingo, which is epoch. An epoch, then by definition, is how many times you go through your data. Each iteration that you do over all your training data is an epoch. So in this case, for example, if you have your training data set divided by ABC, you have to go between ABC, 1 and back, and that's one epoch, because that's all your training data. Okay? That's all. Just to say, like, people in computer science likes to do things in a way that is complicated for everybody else, because this could be called iteration. But no, they call it epoch because somebody was a fan of Star Wars or something like that. Right? So, what's the strategy that we can do to go back? And this is exactly what the loss function means, also called KAUST function. This is a concept that usually confuses people because we were already into deep mathematics with the activation function. And it's like, okay, an activation function, what is that? Is it the KAUST function? No, it's not the KAUST function. Really, it took time for people to actually figure out that activation function is technically a filter. The loss function is the strategy to go back. So the loss function, technically speaking, is how you're going to create a value and decide that that's the path you want to go back. And this is called mean square error, categorical cross entropy, binary cross entropy, and KL divergence. Those things, what it's trying to do is just to adjust the best it can the prediction that you're trying to do to the training data set. So once it goes forward, it's just giving you technically some results. When you go back, it's like, no, we have to adjust that prediction better because we need to go with this line over here. We have to fix this bend over here, blah, blah, blah. And that's precisely what the loss function does. And because you have a bunch of different values in each of each layer, you create a gradient of numbers when you go back, and that's called the gradient. So this value will actually also be dependent on your problem because, for example, if you want to predict a number, you will use the mean square error. If you want to predict what is a cat and what is a dog, you will use categorical cross entropy because those two mathematical things will tell you like, okay, this is a probability for this, or we have these two groups here that we want to separate really well. I know it's a lot to take. It's just one workshop. It takes time to digest. You have to go through another set of hours reading about it because I know I'm trying to do my best, but still is very, very heavy to digest. Yes? Okay, so to determine the question was like how to determine technically the weight inside of the neuron. So the first pass, the neuron does the first try to fit the data into the model. So let's say it draws one line. The activation function tells like, okay, this is a good fit, turn it on, fine. When it comes back, it said like, no, you have to correct the bias or the slope of that line and then move the weight back. And because I'm looking at your mean square error, you are far off any number of different units, so we have to minimize that. And then it's like, okay, this one stay active. The next pass, we have to update this because it was not a good fit. So it has to do that for all the different neurons in all the different layers. Therefore, it's like try to guess which one is being active and not active without a clear path is very confusing. Okay. So I wanted just to mention, like, for example, for backpropagation, one of the most used strategies is this one, the SGD, stochastic gradient descent. So in a stochastic gradient descent, just have to think about it like if you're in the front of a crater of a volcano or something like that, it's dormant, it's not lava or everything, you're going to roll a very small ball, heavy ball over that thing, and you will try to that ball reaches all the way to the bottom. But if you are imagining this thing that it was a crater has different curves, different minimas energy, if you want to call it like that. Basically, you have different pockets, different size of pockets. You have ridges and you have valleys. So the ball is going to be pushed and it's going to roll and it's going to either sit in one of those cavities or it's going to skip it and go forward down until it reaches all the bottom. That's a stochastic gradient descent, explained in a nutshell. So what happened here is like, now you have to understand that this equation that I present you here is actually not that complicated when you start just breaking it apart. The green part is the loss function, meaning the value that it has to minimize. Then the gradient is all these values that you have there, already done by the backpropagation. And then there is a learning rate, which is a famous learning rate that will adjust how far or how slow it goes through those layers to adjust those values again for the weights. So as I'm saying this, I need some water because it's a lot of words. And I know it's very complicated because all these things took me quite a while to grasp it. And I'm just throwing this to you very hard. But, sorry? How is the what? Yes. 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 Yeah, the learn rate is independent of the loss function, you mean? The eta. So the parameters that say that eta, technically speaking, is all the weights compilation and all the bias. I mean, actually, it's like the eta represents the weights, the biases, and the weights, the bias, and that. Yeah, that's it. The weights, the bias, and the iteration. Yes, they are actually sampling the distributions. Well, depending on what you put in depending on your strategy. For example, stochastic gradient descent does that, but for example, the other one that I told you, KL, planar what, it will compare distributions. This one is just comparing like how good is the fit, if I recall correctly, because it's not exactly comparing distribution. It's comparing like how good is the minimum value compared to another minimum value where other things are. So in this case, yes, it's minimized to the gradient, but they're trying to go to the minima, to the possible minimal value. So in that case, for example, it changes when you use KL, because then you will have the distribution A versus distribution B, how well are they actually being compared. So in that case, that eta that says parameters are iteration something is all the weights that you have per neuron plus the biases. So it's a bunch of matrices that are there living, and they have to change value. So yes, it's a very compressed way, but yeah, the eta is that, all those numbers. And then obviously the learning rate will affect the adjustment of those values in these matrices. Okay, well, for the practitioner, let's say for most of the reports that you have to deliver, whenever you are training a machine learning or a deep learning or anything learning, you have to give some performance metrics. So in the papers that I review, I always ask for this, which is a performance evaluation. And usually the reason why I ask is because just right now, all the students blindly train the thing until the end of time. And it's like, of course, either you are in a very rich country and you don't care about it, but where I come from is like, we need to budget the results really a lot. Because if not, you're wasting time for everybody else. In this case, for example, I will always ask like, okay, give me back your fitting curve and your validation curve, because I need to see what happened to your training. In the first case, I put something that says, stop here. And you can see like the training curve, it goes down. The model learns and learns and learns and learns and learns and start updating and updating and updating. So the fitting is better and better and better and better and better to the training set. But when you apply your new model or your deep learning model to the validation set, it just doesn't change. If you see that curve plateaus after the epoch 20, meaning iteration 20 over the dataset, it makes no sense to go forward. The model can infinitely learn from your training dataset until kingdom comes, but it makes no sense because it will not improve how it predicts the next thing. When it sees a new thing, it just doesn't do it any better. Worse, if you see the one that is in the middle, this one that is in the middle, this region that is not between them, no, I mean, it's like if you give the training dataset to you actually can determine this in the program. How many iterations through the dataset you can go? So this guy did 140, more than 140. So it's like at 20, your model is not better. Why? Because you have a validation dataset that is telling you if we exclude that bunch of data points from your training, your predictions are not improving. It should improve, meaning that it should go down. So in this case, you should tell your student or to yourself, it's like, it makes no sense to go to 40 because my model is just learning without gaining anything in performance. So this is why you see it like that. And you see this a lot in the different students that I know from nowadays. But you can activate something that is called early stopping in your code. You can tell your code, if you don't see this actually improving, because stop. So in the other case, for example, in the middle, you have something that will be, technically speaking, overfitting. You have a very sharp decrease in the training, and it goes almost to zero. The loss goes almost to zero, meaning that all the values in the training set are being fitted in the model. It's a perfect fit. Yeah, exactly. Yeah. So yeah, when you overfit something to your training, and then it's like you go to the validation, it's like, but I gain nothing. The model learned perfect all the data points. But then it's like your validation here, it's technically the same. It didn't change at all. It did only 30 epochs, but it's like, nothing happened. Like it didn't improve. As a matter of fact, at some point, it actually went worse. However, if you look to the accuracy, wow, my model is super accurate. It goes to 100%. 100% accuracy doesn't mean that you're, especially in the training set, that your model is actually good. Because, for example, yeah, I train my model here, and then it's like, fine, my accuracy in the validation set, 97. But that means that probably this was not the data set that you need for deep learning. You were just maybe a piece in your PI because you needed to use deep learning. But this is not a case for deep learning. I bet that in the data set here, a linear regression is more than enough. Okay, and the best case scenario, like a real case scenario I haven't found, but the ideal scenario is like you have your training going down closer to 0, and your validation set is even better, is below that. It would mean that there is still data that your model can learn, is not present in the training, but still that if your validation is below that, you're good to go. These spikes that you see probably are because at some point you don't see all the data set and it's not correctly predicted, but still is going down over different epochs. That would be actually a super good result. It's not always the case, but it's a super good result. Okay, so let's take a break before we start this, because I know I managed to actually put all this into your heads in less than an hour. It's very difficult to manage. And I'm telling you this because I spent months learning this thing. So take a breath, please take some coffee, take some cookies, or if you're watching this in YouTube, I don't know, take a sandwich. Yes, one question, tell me. What type of data? I don't know, I just find the plot. For example, this kind of data in the middle is an example of overfitting, but it's not my data. I don't know what they were training on. Yes. Uh-huh. Okay. Uh-huh. Okay. Uh-huh. Yes, okay, so the question is like, if you have previous data, how good can this actually help to predict future data? The stock market is a bad example because nobody can predict the market. But in the same regard, if you had like some kind of a lot amount of data, historic data, so if you have a lot of data from different examples, I will give you this. For example, the vision models. Vision models, like those that are trained on image, in images. For example, I bet that everybody here has Google Cloud or whatever. We have 1,000 photos. Just in my case, I have like 5,000 photos from different things. So I know that if you're a cat lover or a dog lover, you have like 10,000 photos of dogs, 10,000. We have all that to our disposition. How many photos do you need from a Chihuahua, from a Grand Dane or whatever to train a model? That's a different question. But we have historically like a lot of that data. So it has gone to the point like we can input all those data into one model to predict not a new breed, but to know like what breed is that breed. And it's very, very accurate. So the more data you have, classification or regression with a bunch of data that is historically like, I don't know, very consistent prediction of a number, even that is always like a seasonal thing. Weather forecast is a very difficult task depending on where you are, especially because, yeah, we have a lot of data. The problem is to have all the different data fit it into one model, because usually that becomes the problem of how do I use correctly the memory to go over all the data that they have for weather to predict the next few days or the next month or the next year. Yeah, we have the previous data, and yes, exactly. That's the point. If the weather doesn't change drastically, like if you have 4 seasons, it's kind of reliable to predict. But for example, in the case of Jeddah, rain comes suddenly. Like there are examples that sometimes the cloud just appear, and it's like you have then a bunch of data about how sunny Jeddah is, like millions of points, and then you have like 100 points of when a rain happens. And that's the problem with imbalanced sets. Yeah. No, I mean, mostly of the actually. Google releases some kind of some kind of weather model like that you have historical data about certain parts of the world, and they managed to fit all that into memory, and they have been kind of successful with that model. The problem is still like difficult to predict just with deep learning models. You still have to resort to some other prediction methods. The thing for weather becomes easier to predict if it's kind of stable. However, if you have a very strange events, you cannot predict that because you don't have a sample size enough. It becomes actually a problem of, okay, I want to predict rare events. And it's like, okay, how many samples of rare events do you have? And then it becomes like a very small bunch. And it's like, all right, so with that, we cannot use deep learning. If you have a small bunch, just 1,000 points, it's not deep learning. It's not going to help. You need 70,000 points up. You have actually now, you need millions. And even though you have, for example, 1,000 data points with different layers of, I don't know, different measures of humidity, altitude, solar radiance, or whatever, it's not enough. It's just you're dividing the data points into different features, but you still have 1,000 data points, and it's like not enough it's not enough to build a model with deep learning that will predict something better than a linear regression. And that's something that I always ask in the papers I review, like, show me this is better than something basic. And while you have a bunch of data sets about weather, rocks, and other things, people is starting to be interested in the weird and very difficult and very small events. And it's like, yeah, I mean, we could try, but we don't have enough samples. Like, take, for example, the MNIST dataset. MNIST is technically handwriting for 70,000 people. You can go to the history and take probably the writing from somebody 100 years ago. It's different, but still it's a tree. And then I put my tree there, and all the people in the middle, you build a big data set about number 3. No, the thing with MNIST is like they have been iterations of different MNIST. The first one, it was like really clean numbers. And then it's like, okay, let's go for the ugly numbers. Because it's like, my grandfather didn't write the same way, and my grandmother in the same way, and I write the same way. And then it's like you have elongated, different like that, but they are all 3. Yeah, and some are like these, some are tilted like right hand, yeah. Those are included, and they shouldn't be included, as a matter of fact. That makes the data set more robust, and theoretically your model more robust. If you include all these different things that are weird, they actually should improve your model. It's like adding a Chihuahua, which I don't consider a dog, into a dog dataset. And it's like, okay, that's the outlier, but there are enough pictures of a Chihuahua and that's a dog. And we will label it as a dog. It's a strange thing, but still a dog. It's the same thing with weather. Like you need to add a bunch of those really rare events to make it significant signal. If not, the model will not pick up. For example, if we train the dataset in Jeddah, it will absolutely 100% sure will be like tomorrow sunny. But because it's like most of the time across the last, I don't know, 50, 20 years, it's been sunny. And you want to predict like when it's not sunny, that's a different question. But anyway, so, okay. Just let me check something. And please, if any one of you wants some water or coffee. Good, good, good. Ah, okay, yeah. Now, see, yeah, yes, actually, yes, I was going to say that. So Jensen Huang in the NGC has been very entertaining to watch the last years because he passed from being the guy that allowed me to run Doom very, very quickly in my computer to be this financial feature of the world. And at some point, he was selling actually HPC equipment and everything. And now he's into AI 100%. And now he presents robots and he presents stuff that is like, oh, this is the next iteration, this is the next step. And we have to scale up before we scale out. I think that's what he said. And for example, he was actually in computer file. He was, I think this is the interview you saw. In computer file, they asked him like, okay, what do you do? And like he said, now I give the papers to ChatGPT and tell me the main points out of it. And at the end, you have, technically speaking, a scientist there, a specialist on that theme. And that's an LLM running behind it. As a matter of fact, the technology that changed our world is called transformer. The transformer architecture is the thing that runs in ChatGPT, in Gemini, in Mistral, in everything, because they find a way to actually to input all the words. And because we have text since the dawn of time, well, we have text from the last 20, at least 20 to 50 years digitalized. And we have been digitalized more and more and more. They have a huge training dataset that is all words, and now they can easily predict what's the next word. But most importantly, now they have this reasoning, quote unquote reasoning, of, okay, find me what are the best important points. And usually there are some set of words that we humans use to highlight something, especially in papers. In papers, we always want a remark. And so it could be that we have 1,000 different ways to say it in a paper, but still, like it's 1,000 times repeated all over the different papers since, I don't know. Yeah, I mean, yeah, it's like, yeah, it's 100 keywords, but it's like, even before ChatGPT, we were in my PhD and we were always laughing like, okay, let's bet how many times our PI used the word innovative. And it's like, in the paper, in the next paper of the next student, we have this tendency as humans. We have a writing style, And I bet that your PI, we have this preferred word to highlight this. And then to sell the idea or to remark the idea. So if you do that, and he's probably not the only one, you can feed it, and then in theory, it will give you back the content. And it preserves the idea of the content still in the memory, and you can query that. And yeah, it works. Okay. Yeah, I mean, it's been done. As a matter of fact, the first and the only software that has proved that AI can solve scientific things is in biology. It's AlphaFold. AlphaFold is the only software, or it was the first software to actually solve a scientific problem. Okay. So thanks to the efforts community, because in biology they have these critical assessments of different things, and because biologists are very prone to give the data out, to keep it in the public, not like the chemists, by the way. AlphaFold was able to be trained in a massive number of sequences that are words, in a complete good number of three-dimensional coordinates that were inputted into different embeddings, meaning like they were translated to something that the computer could read. And they were training like, this is your starting point. These are the key points in that starting point. This is how it looks like, and you have to integrate it like this. And then it goes and predicts one unit. And AlphaFold is very good at predicting 1 unit. If you give him a string of letters, it gives you a three-dimensional thing at the end. And it's not 100%, but it's like 98% accurate. So it actually really solves the problem of, if I have a string of letters, how does it look like in three-dimensional stuff? That was the question. It was solved. The PIs were not happy because now they're out of jobs, or they have to find a new venue to actually explore. Some of them were actually very good at that. But it's really, really good. Now, we went to the details of, can this be now used for another set of problems? And it's like, all right, it solved the main problem that it was set to actually solve. For the other ones, we can still improve it. And then it's like, okay, now we have the blueprint of how to do this. Now we can take this into the next level and switch it off, change stuff, make it faster. Now it's super fast. The question now is, okay, where do we go from here? And then in the field, people is like, okay, we have to move into dynamics. Or we have to, no, we have to bypass this and now do another thing similar to this, but with this information. It depends on field to field. But for example, we're still waiting for that kind of model in weather or quantum physics or what have you. All right, let's start, because the next one is going to be painful. So for you that did the Git introduction, was the same thing, please go to the wiki page. Now instead, wiki page, training events. In the training events, you will find this introduction to PyTorch link. Okay? So once you're there, you will find this beautiful web page. And again, you will see there that I put these slides there. There is the Etherpad there, but it wasn't a success last time, so I don't think we're going to use it this time. But what I do want you to do is to try to jumpstart the binder or the class hub. I don't know which one is going to work, because I was testing this morning and one of them worked and the other didn't. So for example, for binder, you will find, technically speaking, this, why I say technically speaking all the time? So you will find this repository there, and all the way down, you will find that tag that says KAUST binder. Please start it now. And for those of you that are looking at this in the web page, please start the other one, the launch binder normal. It will take a long time to start, probably. Now, if you're in KAUST, if you're a KAUSTian, we can do another thing. While you, okay, this is also the, this will be recorded in the KAUST Visualization Core Lab YouTube channel. Like and subscribe. Remember to give us our comment. This is not sponsored by anyone but KAUST. So if you want to tip us, you cannot. But anyway, you can find there all the information and how to set up this kind of environment, for example, and use other apps. Okay. So, as a matter of fact, let me give a pause here. We're going to check. Okay. So, like I was saying, please start now that binder because it can take time. But for you people in KAUST, you have this thing here called Class Hub. Okay. In the Class Hub, you have to go all the way down here and say begin course. And hopefully this time it will work. It will actually ask you to log in with your GitHub account. So just let this run. We will see if it works. After you have your GitHub account, please go into this link. Put your GitHub ID here and submit. Okay, one more time. Here is a link to Class Hub. You go all the way down and you put begin course. It will ask you to access. Please, after you create your GitHub account, click here and it will give you this Class Hub request. And now you should be somewhere here. Oh, start. Okay, so for the binder, hopefully if this doesn't work for you or you don't get access, let's go to the binder. You will see this repository here. It's all the way here for KAUST is something that says binder hub. Click there. You will see the thing starting, okay? Or here in the binder. But this binder here is for external people. This one for KAUST people because we have the resource here. A little bit small, but it will work. And then you will land in a page like this. If you're not there yet, you can click here, okay? And you might see this, KBL binder serve. Enter there, and you will find a bunch of data, hopefully. Let me know when this ends. Because it takes time because it has to, technically speaking, install all the libraries. So better to start it now. Where are you, by the way? Only 2 files. Okay, you are here, right? So if you are here, you go to KBL serve, and it should have something there, right? Yes. You are here with these two files here, right? So it's still running. It's not running. Okay. Does it set binder? The KAUST binder. Okay. So here. So this has to happen. Then it says launching at some point, and you're here. Okay, perfect. That's what I want, because we're going to use notebooks. Okay. In notebooks, you will find there all the practice that we're going to use. In the KBL binder serve, it's the same thing. We have some notebooks here. Okay. So I hope that all of you are now in that resource. Anyone with a problem? Inside of the KBL, you don't have notebooks, for example? Okay, try to go then to the binder. Okay, so far so good? You okay? You okay? You okay? You too, over there in the back? Yes? How about you? Still working? Yeah. Yeah, put your GitHub account there. Authorize KAUST GitHub. Isn't it? Okay, so go to the binder hub. So that's the binder. Jupyter hub. Now go to binder hub. Yes, there, here. And then go all the way down. And there, the KAUST link. Let it see through, and you will find there the same material, okay? And then into notebooks. Okay, fine. Awesome. All right. So this is the last bit before we enter to the notebooks, okay? Because I wanted just to chat with you about what you need. This is, technically speaking, the structure of a code in PyTorch. So first things first, you need to import the libraries. In Python, you always import the libraries like this. So you import Torch, you import NumPy, you import NN, which is a model that has neural networks. And you have to import, for example, data loaders. And please do remember to set your random seed. So here you have 2 lines that will technically control that randomness initialization that I talk about. If you do not do this, every time your code will be a different result. So you can change the numbers there. I put 42, but you can put, I don't know, 101, or you can put, what's the answer to all life? Hitchhiker's Guide to the Galaxy. 47? Okay, jokes aside. Anyway, so you can put any number there that you prefer, but this is for you to control. Next thing is that we're going to create our datasets, our training, our test dataset. For example, in PyTorch, they have always imported historical datasets. You don't need to download them from any other source. PyTorch already have this preloaded. And this is the way you write it. It's like, okay, I want to create my training dataset. You import the datasets and you call it MNIST. And then you say, like, I want everything to be in a folder called data. And it will be the training set. And please transform it to a tensor. Meaning that PyTorch will do everything for you from the starting. You will, technically speaking, just tell him, like, give me the tensors already done so I can input this into my computer code. And you can do this exactly the same for the test or validation dataset. Okay? You can find this in the documentations. There is a lot of documentation about PyTorch. But this is, for example, a very easy way to import right off the bat 70,000 different images and divide them into datasets. So you will see this, by the way, in the notebooks. The next thing is that you have to, technically speaking, tell the computer, like, I want to go over my datasets made in different batches, in different sections, and then just tell me what's the shape. This is a checkup, okay? You will basically chunk your data into small batches so it can be fed into the computer memory. Otherwise, if you don't do that, your memory will blow up and your program will stop just because it cannot manage that much information at the same time. This is why actually NVIDIA is actually making the big buck, because they have been working on expanding the memory so you feed more data into the algorithm. So this is very important, and I wanted just to check this beforehand. When you are writing a deep learning program, it has a skeleton, okay? That's why I put this schema there alongside the code. Now, when you're in PyTorch, you can tell already like, hey, I'm going to work in images, so I need convolutional things, because convolutions are better for images. So I call the convolution here, and it's right here. This is the architecture flux of information. Like you have an image, then you have to convert that image into different matrices that will actually expand the number of channels, quote unquote. It passes from being 1 to 16. As you see here, the convolutions, technically speaking, start to divide your data set into more things that it's going to explore. But what I wanted to highlight with the different colors is like, for example, you call PyTorch, and that call in PyTorch is here. As a matter of fact, you have to define what is going to happen the way forward, the flux of information. So these are your layers with neurons, and this is the flux. You see here, you have the first convolution here, the second convolution here, then you have a dropout thing here. Dropout is a technique that will allow you to avoid overfitting. You can look at it later, don't worry about that now. You have other layer here that is fully connected, another dropout, and fully connected. What's the 1 here, there, and what's the 16 there? So what happened here is like you input a grayscale data, like the MNIST dataset. It's an image with only gray colors. Oh, well, black, white, and gray. So you just have one matrix. 28 for 28 is the number of pixels. So it's one channel and 28 by 28. Then the convolution technically takes some of those pixels out, and it spreads them also in different matrices, and that's why you end up with 16 different channels. Yeah. 3 and 1, where? Where is the 3 and 1? Okay, in the code. Yeah. Okay. So yeah, when you go to the documentation, you will see it more in detail. But it's like this is the input number of channels, and this is the output number of channels. Then this is like how many I'm going to lose, if I recall correctly. Let me check. But I will tell you later. The thing is like the output channel is going to be the next one input, and then it's going to output more, and these 3 and 1 remain the same because it's the same rate. I think you lose. Yeah, let me check. I will tell you in a bit. But anyway, so this is the skeleton. This is why I wanted to present you what you're going to see. The 4-line dropout. Dropout onto the thing is like dropout mean like how many of your neurons are going to be deactivated, the percentage. So in this case, the first dropout layer is going to randomly turn off 10% of your neurons. And in the next dropout layer, you're going to turn off a quarter of them, just randomly to avoid overfitting. It's a random, the dropout is random. It will just turn off. It could turn off good fitting neurons or bad ones, but you don't control that. You just turn them off, just to make the sample more random. I hope this is still on. Yes. No, you want this to be random. Because if you start picking up, you will end up with a lot of bias inside of your model. So this is why it's random. That's how many times do we have to fit the, exactly, good question. How many, well, before we fit all our data, we still have to define our strategy. We have to tell what are we going to use. For example, I told you about the cross entropy. We're going to use the SGD. Now you know that's the strategy to backpropagation. You have the entropy as a loss function, which is where we're trying to minimize most to the zero. We have to tell also usually what device are we. Could be a CPU, could be your Mac. The thing that we have runs in Mac, in CPU normal or GPUs, but it's better. And then you don't have to work yourself out too much about what's a COMNet, but what you have to tell the code is like, use the device I have because that device is the fastest. So this part of the code is kind of relevant. You can see more loss functions and more optimizers, more strategies on the official documentation. Yes. Yes, yeah, it started the PyTorch. In the first, as a matter of fact, I think you lost that one. But look, the starting. No. You import Torch, and it automatically, because you're in Python, it technically speaking is just like, okay, the libraries in Python that are called Torch is PyTorch, but this is PyTorch. Yeah, I mean, at the end, it's like a naming problem that they didn't solve because they took the original PyTorch, they took the original Torch and then implemented in PyTorch in Python. It's still called, in the code, it's still called Torch. Yeah. Exactly. See, if you're using another thing, it's not PyTorch. So, yeah, I know, ridiculous. Anyway, so here after the skeleton, you define the strategy, and then you have go over your dataset. And you have to go over the dataset several times. So for training, usually you want to go over all your training set at least once, but usually you have to pick between 10 to what have you. You don't know how many iterations you have to do of training actually. And this is why you see a lot of, you saw the example of 140 steps going over your training. You don't know when to stop until you have your validation data. But this is what it basically looks like. You define a for loop. You go for every step, every subsegment of my data, pass it to my model, and you see it here, then activate the loss function, calculate, then do the backpropagation and adjust those models, and then start again, and again, and again for each of these, and it goes just to basically a for loop. And then you do the same for your test set, but your test set will tell you actually what is going on with your validation. The difference between here and the past one is that we have this torch no grad. This will actually tell your code like, do not update the weights. Use them as they come and evaluate these data points here. That's the main takeaway of this one. And then, of course, you can put how many times you want through it. We're going to use a very small number of epochs because it doesn't make any sense to go further. It will come back as a very low performance model, but you can later in the day go crazy and put, I don't know, 500, which makes no sense. But at the end, it's like you can do it any times just by defining how many times you want. You have the control of this. And then you can save the model. Okay, with that, that's fine and all. Now let's go back to the notebooks. So in the notebooks, you can if you don't know NumPy, you can practice NumPy, but the real thing starts here with the Tensor basics. Okay, so let me show you. one of the things. You will put your code here. If you're not familiar, by the way, I'm assuming you're familiar with this. This is a Jupyter lab, and we're working in a Jupyter notebook. So we have two types of cells there, the markdown, which is the text you see, and the code cell. This is why I put code here, okay? So for example, I just put step 1 in performance standard import torch and numpy. You have to read import torch and import numpy as MP. And then you can basically run that one. It will show an asterisk that is running, and it will say, okay, that's there, good. Now, for those cells that you do not know what to do, like for example, set random shifts for PyTorch both to 42. I gave you that, actually. If we go to this, is Alt-Enter, but you can run it with this small button here, okay? In Windows, what is it? Because in Windows, I'm not sure. For me, it's Alt-Enter to Control-Enter in Windows. Okay, Control-Enter in Windows. In Mac, it's different. Okay, Control-Enter then. Perfect. So in this case, for example, I gave you this one. You don't remember how to set the random results? You can click here in Solution and cheat. Okay, so you copy this thing here, and you can run it. And it will say, okay, torch generation, blah, blah, blah. Now you have set up your seed. What I'm telling you that this solution thing is a markdown cell is because it has this format here that looks like HTML. So whenever I want to see the solution, I can just click here, copy this, and put it here. And then, for example, if you include this here, yeah, it will not, it suppress the Jupyter app, okay? Now, for example, create a NumPy data array. In this case, data MP array equals MP. If you are a little bit lost, for example, you can do MP tab, and it will deploy a menu. Okay, that's the power of Jupyter notebooks. It will help you. Jupyter always will help you. So you can put, for example, array here, and it will autocomplete array. I'm going to put here the data equals 1, 2, close, and then 3, 4, like that. And then I'm going to call it like this. This is my style. Unexpected indent, meaning I have a space here that I have to kill. There you go. Is my solution similar to this? Yes, pretty much. I didn't put print. Okay, let's put print and run it one more time. MP array. And there you go. Okay. Excellent. If it's like that, excellent. Shift and enter also should work, I know. Yeah, okay. How you like the notebook so far? It has all the solutions there. So we can go through them together, or I can give you 5 minutes if you want to do it alone because you're grown-ups. This one is a matrix, as a matter of fact. Yeah, great question. What you see here actually is just a matrix with 1 row, 2 columns, two row, 2 columns. This is the NumPy way. And this is why we're going, if you go down, you will find that we start using tensors. Tensor is a different type, but still is matrices of matrices. But for NumPy representations, it's better to tell like, this is a tensor. And PyTorch actually will tell you, like in here, you can create NumPy, you can create tensors from NumPy, and you will see it here. Now I have a problem here because this should be data. Okay. So you see, torch long tensor. If I do the same thing for this guy, type MP array, there you go. Missing one, okay. So in this cell, we're actually doing a NumPy array, and here you have a long tensor. And this is what Torch actually like. PyTorch will already tell you like, okay, yeah, we're based on NumPy, but we prefer these to call like that for classification purposes inside of the computer. So for example, create tensors 1. Okay, so you can click here and it will tell you, okay, you can go here. And this is how you actually declare Torch 1. This is the actual documentation of PyTorch, okay? So for example, you can say like, okay, Torch 1 input. I can copy this as a matter of fact, run it here. And you have a tensor like. Now it's telling me use X data, fine. So X data. And I have it like that. And if you are also wondering, okay, here is the solution. As a matter of fact, let's print it. X once equals once. Learn to type. So here in the input, we can change it to whatever you want. Let's say like 5 by 13 just because, and it will create very easily a bunch of ones in a tensor form. Now, I want you to notice like Torch can have a lot of these kind of libraries that will help you. It can create zeros, it can create ones, it can create random numbers already in a tensor format. Okay? I like it because it gives you everything. So, for example, let's go to random like documentation. It will tell you, okay, we have something called random like. This doesn't have actually any example, but I can copy torch rand like, paste it on the cell, and I say, okay, use X data. And then it's telling me something. You need to use something else. Okay. So here is the input and memory format. Equals torch dot float 32. I still doesn't like it. Great. So I failed twice. What happens? What's the solution? It's D type. So if I do this equals D type, let's actually do this too. Print. Let's define it as xrand. There you go. Yes. NumPy has the same thing. And you can go all the way here. I mean, you will see that we have an example of how to slice this type of arrays there. Very easy. And you can just code it. And if you don't know how, I will give you the solution there. Are you done with notebook 1? Are you done with notebook number 1? Everything is smooth? Good. Now let's do operations. So the next, as you can see, is PyTorch Tensor operations. So as always, import torch. You can put it here. Then detect the device and go step by step. Okay? Let me know if you have any problem with any of the cells. Okay. So far, so good. All cells are working. At least in YouTube, they tell me they do. Okay. Now, if you see it, I display there also basic operations. If you have some experience with Python and NumPy, you will see that this is pretty much the same thing. You can add, you can subtract, multiply, divide, get a power, get a sum. This is normal things for NumPy. They just actually implement it in PyTorch the same way. Under the hood, they are doing the same stuff. Technically speaking, very similar, but PyTorch can actually do the tensors. And just because I like to torture you, just remember, you saw this at some point in high school. Dot product. Yes. What happened? Okay. Which? Number 6? Calculate the dot product? Interesting. So let's go back and recall what is T1 and T2. I am going to cheat, obviously. But I cannot forget to import torch. This part here is actually pretty important. When you're working with GPUs, or if you're working, for example, in a Mac, you will have to tell PyTorch, like, use the Mac thing, which is this line. Right now, we're using only CPUs, which is great. Tensor. Okay. Over here. Print tensor, this one, for example. Before? Mm. Here. Yes, you can define this. Yeah, the torch.1, it will just create a matrix, the tensor I'm telling you with these dimensions, all one, everything. You mean the values inside? Yeah, they are floating point. They are float 32. Yeah, you can actually, like in the previous one, we changed the type because depending on your computational capabilities. Now let's explore this problem here. One detector expected. Okay. So if we change this to this, doesn't work. Nice. Interesting. So he doesn't like it. 1D tensors. Okay. Then tensor. Got 2D tensors in that regard. Tensor here is. Okay. Yeah. Like, I don't like it. Yeah. It's about that thing. Nope. Not about that thing. Yeah, no, it's supposed to be 1D. Yep. Yep. That's correct. So for example, these should work. Over here. There is a tensor. Is 2, 3 to 1. Yeah. This. If I do that over here, defining these. I wonder if this works over here. Wait. Let's silence that. 3 equals tensor. So. Yeah, you have to like 2 layers. Yeah. Yeah, like she said, it's a matrix. So yeah. Anyway, if you reach all the way to this point, that's okay. I will fix it for the next one. This is actually, like I said, this is the first experimental one. Thank you for pointing out all the details. All right, go to this one. Number 3. Actually, I like this one. This is also from the PyTorch original documentation. Automatic differentiation or autograd. What does that mean? So remember that you have to do backpropagation at some point. Autograd will do it for you. And you have the same thing. As you can see, as I was presenting in the slides, you have an input, you have your parameters, the weights and biases. Hence the name W and B. And then you have to adjust it to the loss. So this, I think, in my opinion, this is an important exercise because it allows you to actually see what happens into the gradient. It's quite simple, not so much you have to do, really. But it also plans, basically, you are telling the computer, like, this is your plan. This is what I need you to start computing. So go through it. Let me know, again, if you find another cell that doesn't work. Very important to me. And it's very important for the future scientists that are coming to this thing. One. All good? Can you hear me? Yes. Good. So as you can see, this is very, very verbose. I put things here that people from PyTorch also puts. But more importantly, I think if you want to go to the details, to the nitty-gritty math, this is the important part, like the Jacobian product. Actually, for me, it was clearer, like what's going on with the gradients when I saw these equations. But technically speaking, this is what behind the hood happens when they are calculating the gradients, all the weights and biases adjustment. So, I don't know, maybe I'm too nerd, but I think it's beautiful. Okay, so all good with the notebook? Were you able to reach all the way down? Okay, we will wait a little bit. This one is not working either. Huh. All right. Which, by the way, don't worry if you, like, if you go to the repository, you will find these notebooks if you want later to just check them out again. So all our resources are available for you. Let's cheat. Of course, I put there the solution and I hide them in order for you to try it first, fail at it, and then look at it. Yes. Yeah. Get the value of loss. I didn't include the loss here. Yes. Yes. Yes, it's right into memory because you are technically, what is happening is like you are giving the information about what is going to happen, like the computing graph, but this is why we also pass everything to the memory, because theoretically, if everything is in the memory, if the data is in the memory and the model is in the memory, the transference of information and the flux goes faster rather than from the device outside of the memory into the memory. This is yes. Yeah, I mean, everything you can tell, like you either have a gradient or you lose it, or you don't modify it. Yeah, it's like this is like where are you going to place it? Just right now it's not computing. It's just like allocating the space there to do the computation. Yeah. I don't remember if I put it over there. W is not there. Trying to backward through the second time. Yeah, that should happen. Okay, try this. True and false, and then good. Ah, good. Okay, and this one. So far, so good. So this one fails for you too, right? Mismatch in shape. Ah, curious. Torch side has blah blah. Okay. I will have to fix it later. Good. Okay, let's continue with data loaders then. Curious, but good. So in data loaders, you will see basically that PyTorch gives you everything back. We're going to basically load the CFAR 10. This is another dataset, not the MNIST, but the code is the same. I don't remember what it's made of. Let me check it. CFAR dataset. Color images in 10 classes. So this one is another one that is pretty famous. Yeah, it's a objects database. It's a bunch of different images of color things. But it's like 10,000 categories, if I recall correctly, something like that. But the data loader notebook, technically speaking, give you the same kind of writing that you have to do for any of these datasets that are allocated in datasets from PyTorch. I think I put some link here. No, I will put it later. If you do PyTorch datasets, maybe here, datasets and data loader. Okay. Go there. in datasets here, you have a list of all the different datasets that automatically PyTorch can give you back. Like you have these distilled forms of CFAR, you have food, naturalist, MNIST over there, optical flow, stereo matching. All of these, you can call it the same way we're calling it now in data loaders here. For example, this one we'll call fashion MNIST, which is technically speaking a bunch of images in black and white about shoes, jackets, t-shirts, and other stuff that is fashion. So the way you write it is basically the same. This works for technically everything, and then you just have to call it like this. So if you do this, for example, of course, I have to first, where is PyTorch? I have to do this. Define A in line 6. 1, 2, 3, 4, 5. That's all. 1, 2, 3, 4, 5, 6. Ah, of course. I should have, this is not silenced. Yeah, so this is the problem. Okay. But now it's going to tell you it's start downloading stuff. It will create here a data folder. It will start downloading things there. Done. And also it will, technically speaking, will transform it for you. The transformation that we are actually asking is just pass it to a tensor. Transform. Where is it? Ah, I ate it here. And ate a T. Files already verified, and now they are already done in the memory. And you can do a bunch of other things, like you can flip it randomly, rotate it randomly, pass it to. There is a lot of different things that you can do to the data before it gets to your memory. Very easy. Okay, please go ahead, check it. And if something failed, let me know, because these things have been failing. First iteration always does. This is a short one, if I recall correctly. The data loaders are very short. Okay. Where? Data loaders. Exercise 4. This one. Let me see. Exercise 1. So here. Okay, let's check it. Where? Aha. Let me check. Okay. So there is a thing. You have to import Torch, and then from Torch pictures, import. These 2 lines are missing for you. I need to start a small bar that says like downloading. Yes, Torch Vision has different things, especially datasets, or it just calls the repo where they have it, and then they just put it in your computer. It has a lot of data images if you call datasets, and then there are other things that it can do, because if I recall correctly, Torch Vision also allows you to do transformations and some other different properties that it has. Transformations are the ones that are actually the important ones because they are focused on all images. So the rotation, the clipping, and everything is for data augmentation. But those are operational hard coded there. Yeah. Did it fix it? No. Curious. Okay. Yeah, you have to this line define. Just erase it. Run it again. Yes. That will the hashtag comments the lines. Yeah, but good to know. All these little problems. So next time it will be smooth for people to actually look at it. Long tensor is a data type for PyTorch. There's an error in the end. What does the error says? Oh, okay. Could be. Let me go to that part. Let me see. Now it works. Okay. Is it on the solution? Oh, it's missing. Okay. Nice to know. So you went all the way to create custom datasets. You're in this cell? Oh, in the first. Okay. Okay, okay. Yes, there is a missing T here. Okay, I will fix it. Thank you for being the testers of the code. I really appreciate it. Okay, the last one, this exercise, we will skip it. The exercise optional. Because the path to the annotations is not where it's supposed to be. But if you reach all the way here to the custom dataset, to the exercise 6, you're good to go. You can pass to the next one, which is building models. Okay, here is where actually the fun starts, because this is the one that will tell you, or let's say like these last two notebooks are the ones that you are most interested in, because the first one are training, technically speaking, just for you to get a feel of what you can do with the libraries from PyTorch. This one of building models is how you actually call PyTorch to say, I want a neural network that looks like this. And the next one is like, all right, I have my data, I have my model, now training. So go through this one. It should be pretty straightforward because you have to basically import all the libraries, Torch, NumPy, I think Torch Vision, the solution is there. And then you have to actually tell where the device is, again, like where are we using? In this case, we're using CPUs. It will default to CPU. It could be CUDA if you're using a GPU, MPS if you're using a Mac, XPU if you are, I think, in Google Cloud. And Meta has one that I'm not sure what is it. XPU is Intel, but probably it will be phased out at some point. So anyway, when you go, for example, to this, you will be actually using now the PyTorch library to build a neural network. Because you're going to tell it, like, I want my neural network to look like this. I need a layer that is flattened, a layer that uses a sequence of things that are linear. Then you will use this cost function. Then you, again, linear, then another one that uses, again, a mathematical function, and then linear. And then what happened when you do this forward? So these are the two basics part of the skeleton. Like, what do you need? The layers, and in what order? Now, it's very easy to do this in also in TensorFlow, because it also have a sequential module, because sequential means like one after another. There is no skipping, there is no nothing. It's just like step 1, 2, 3, 4, go forward, and then you will have here how to make a prediction. So this one and the next one are the fun ones. So please try it, and let's check if another cell fails or there is a mistake. In exercise 2, there is no code. Yeah. Okay, so you can put more code with this plus sign, or Control N, if I recall correctly. Let me see. Oh, not Control N. N. But this plus sign will add a cell there for you to put the code. Like I was telling you, like it's the activation function, if I recall correctly. Yeah, this one is the rectifier linear unit that I was telling you about. So it's a, yeah, I said it was a cost function. That was a mistake. That's the activation function. No, it's a different one. But think about the hyperbolic. Think about the Cartesian. What the ReLU is like, every value that is in the left side, in the negatives, is given automatically a 0 as an assignment. And if it's beyond that, it's a positive, so the neuron will be activated. So you can actually find the equation. It's very famous. So it's just a hard cut between like what's activated and what is not. Yeah, it just goes from 0 to 1, if I recall correctly. Yeah, this is the activation function. Yes, like that. So positive goes fine. Anything positive goes fine. So any problem with the cells so far? Yes. Which one? Exercise 2. Okay, let me check. We import the functionals. Okay, so let's kill this by just putting there this. Also, XPU doesn't work. Fine. We can erase all this. Yeah, for the second one, erase MPI and XPU. This version of PyTorch doesn't recognize them, so let's keep just MPS, CUDA, and CPU. And it should be the resulting device, CPU. CUDA and MPS. You can yeah, you can technically also tell it like just CUDA. But out of the solution, these two, kill them, erase them. Okay, I will modify that one. That's good. Now let's copy this into this cell. That's fine. and tell PyTorch, put my neural network into the device. So this is the neural network that we're going to use for this specific notebook. Very simple, sequential, and pretty straightforward. Then we pass it to the device, whichever is available. Use the model, we pass it to the input data. Okay. Let's see if this works now. Nice, it works. So here what will happen is like we create a random input, it's a tensor. We are using our model and we're basically predicting something, logics, meaning that it's 0 or it's 1, what it's doing. And then give us the probability. We're going to apply something that is called softmax. And we end up with basically what could be a prediction. But if we do this only, I can show you, we have a tensor with different probabilities. What this is doing is just give me the maximum number once you sort those values over here, and then correlate it with whatever it's predicting. So this thing is predicting basically a number 2. That's fine. Predicted class. This is, yes, I did this. Perfect. Okay, and then, and I guess we have to do this. And this flatten over here. What happened here is like we created, technically speaking, a random tensor. Which one? Exercise 3. This one? Down? Okay. You mean this part here? Or this here? Oh. Okay. Ah, here. Pass through linear. Okay, let me catch up. This is flattened. Yeah, you have to put hidden, just enter here. It is just an error here. It would be like this. Now, always tell him the device, where are you working? Because if not, it will default to something that is CPU. In this model, it doesn't matter, because it's, but if you need like more power, you need to tell him like, go to GPU. Which one? This, exercise, the flatten. Where is flatten? Yeah, here, yes. Flatten. What happened is like flatten is an operation that takes all the columns from the image and puts them into a large, really large column. So instead of having like columns and rows, it just creates one big stretch of numbers. Yeah, in matrix multiplication. Yeah, exactly. You're basically converting a matrix into a very long vector. That's why it's flattened. Well, it's called it flattened because it's apparently always using into using matrices and reducing them to one linear vector. Okay. If you arrive to the last cell with any other problem, go to train models. Now, I really like this video. This is why I put it here. You know, for example, three blue, one brown. They have they have the best explanation of how backpropagation works. Yeah. But his videos are so educational and so beautiful. So if you have time and you have more, I guess you will have a lot of doubts after everything I said. Go over this video is beautiful. But now that you're going to train, this is exactly what we all wanted, to train a model. Okay, so go over there, train your first model. So I was very tired when I was compiling this, so I did some assumptions here, I guess. But please let me know if everything goes smooth. No, all the data sets that we have, even though they are like 70,000 points, they can be downloaded and fed here. Those are actually now the standard to learn because they're super quick to download and process. Data sets that are too big to handle for classes, for example, the AlphaFold data sets, they're massive, impossible to fit them into a small resource like this. Or, yeah, if you are OpenAI and you want to train into massive data sets, I don't think YouTube can be fitted into a notebook. Which exercise are you? Perfect. So let me check. It will take a bit of time, but as long as you have the asterisk there, star is in data. I put things here, there. Yeah. I already finished. If you have a 2 here, like it's 10% stuck. Okay. In that case, you could restart the whole thing. Like this, with this symbol here next to stop. Restore the kernel. One more time, load the libraries. Then when you have this, in my case, because it was already downloaded, it goes super quick. So is it stuck for both of you? All right, restart the kernel. It went through? The other modification we could do is like instead of doing dot dot data, you erase one dot and it will download it in the data folder that we have here. And it should start like that. Extracting, downloading, extracting, downloading. Yep, mine went again. So if instead of dot dot data doesn't work, kill one of the dots, and just do dot your work. Okay. You go ahead and keep training. Line 2 again. No, the device is in exercise 1. Yeah. For this one, please remove these two. Or comment them, yeah. Whatever you like. Because they caused problems. Well, you have these materials free. You can always check them out later. You can use YouTube. You can use the binder pub again. It will be there. Thank you for coming. And I hope it was useful. Now, for example, where are you stuck so far? Where did you give up? Cell 1, cell number 2. Okay. Okay, well, see you later. Okay, so once you run this, you are setting up basically the device and the neural network that we did in the last section. If you notice, I'm just redoing what we did in the other notebooks. Now, here very quickly, we're going to just use these parameters. We're going to use 5 epochs, meaning 5 iterations over the whole data set. Well, actually, it's not that small. In theory, the smaller the learning rate, the slower the algorithm goes, but you get the better fit. Yeah, it's like go over quickly over 1,000 parameters and adjust them. Well, the learning rate is something that you have to actually play with to know what's the best learning rate to update the model. Yes. It's a variable that we can change all the time. As a matter of fact, it's part of the variables that you have to try to find the best number. Because epochs, you can put whatever number of epochs you want, but the learning rate is how fast or how slow is the update of all the parameters. 。 yeah, we're updating basically the weights and biases for all the different. Yeah, so this is like for us basically telling like go either very fast over all the things or take care. Ah, okay, I understand. Okay, you got me there. I don't know if it's about like magnitude of fast or speed. Well, if you remember the equation, it should be how much, but because it's updating a gradient, it's like that affects the whole set of different weights and biases in the network. So as I've been thought, like the learning rate is go through each layer this fast rather than change the magnitude. It's like the learning rate should be controlling the how fast the algorithm, for example, the stochastic gradient descent, is adjusting everything. How fast is the parameter optimization? Meaning like your strategy is either slower or faster. But I have to check that. So I will be actually studying that so I don't tell lies. Yeah, I mean, yeah, yeah. I mean, in that sense, it's a magnitude, but also like what you tell me. If we like you're telling me like if we are, for example, talking about SGD, it's like okay, go like this very slowly, checking out, or go over here, over here, over here, over here, and then like go up, go down. Like that for me is actually speed. But yeah, yeah, it's a tricky definition. But like usually learning rate is thought for everybody to be defined as how fast your algorithm learns. But that's the high school explanation. Okay. You define trained already? Okay. Now, if you reach this small cell here, it will start training. So you will see there, for example, a number. Like in epoch 1, it's calculating the loss, meaning like, remember the loss, we want it to be as close as 0 as possible. It's a very small change, but next to it, you will see how many of the training set is actually being fed into the algorithm. We started with 64 images. Now it's 64 images out of 60,000 images. So the first epoch takes a while to go over the whole training set, and then it's outputting like, okay, we have accuracy of 23. And the loss is 2.6. Okay, still not 0. Fine, but that's the first round over the dataset. So the next round is already 25. Okay, it's even worse. No, sorry, accuracy increase, 2%, fine. But again, it went very slow. But it's over 70,000. Well, it's 70,000 because we have training set and test set here. So in any class, they will tell you the longer you train your model, the better it is supposed to be. But that's not exactly true. I already told you about overfitting and underfitting. So if you reach this part, you will see that the accuracy is slowly building up. So this is why people put like 5,000 epochs. Now, don't do that. Searching PyTorch for something that is called early stop. So once your accuracy or your loss doesn't change, doesn't go to 0 anymore, stop the algorithm, because you're wasting your time and probably your money if you're paying for the GPUs, for mostly your time. Okay? This next step is the last thing that you want to do, which is saving your model. So once you train something, this is the part that is like, okay, now put this here, and all PyTorch models by convention have model.pth for PyTorch. So this one has two ways of saving. There is people that save all the models, or there are some people that save some part of it. You can technically do whatever you want depending on how big is the model. But these weights, for example, are the so-called weights that, for example, Llama lets you use, lets you adjust. You cannot change the network, but you can change the values of the weights and biases. So, for example, if you're working with the so famous LLMs now, most of those that are open source just let you play with that. Some other models that are proprietary, they don't let you play. For example, OpenAI, which is pretty close right now, doesn't let you play with ChatGPT model. It just lets you use it, lets you predict with it, but not adjust it. So this is pretty much the difference in types of saving. But if you reach this place in this notebook, thank you very much. You have been awesome to be here to put up with me and to testing the material. Because as you said, you're the first to actually test it. And I hope it was clear for everybody. Or at least useful. If not, I'm sorry. But I did my best. So thank you very much. Any more questions? Any more comments? Okay. If not, thank you very much. Now, lunchtime. Thank you for the session and see you later.